Usually when we look at high-end manufacturing, we expect precision.
Right. Yeah. Pure engineering perfection.
Exactly. You think of like pristine robotic arms, lasers, these completely sterile environments where you just punch coordinates into a keypad and the machine flawlessly mathematically executes.
Yeah, it's a comforting image, for sure.
It's binary, it's clean, but then you actually look inside one of these
Oh,
machines.
and it's a completely different story.
It really is. Specifically, a five-axis machining center, the kind of multi-million-dollar equipment shaping aerospace turbine blades or titanium medical implants.
Yeah.
That illusion of a sterile environment just completely
Oh,
vanishes.
yeah, absolutely.
Because the reality is incredibly messy. The entire cutting area is just violently flooded in this milky, high-pressure liquid.
It is the absolute definition of a chaotic environment. I mean, what's happening inside that enclosure is essentially a contained, high-speed collision between different metals.
And that brings us to our mission for you today. Welcome to the Deep Dive. We're looking at a stack of technical sources covering a topic that, well, it might sound highly specialized at first glance.
A bit.
Yeah, cutting fluids for five-axis machining centers. But I promise you, this is secretly a fascinating study in extreme physics, delicate chemistry, and really high-stakes problem-solving.
Yeah, it's not just a casual accessory.
Right. We are going to unpack how this seemingly simple liquid is the unsung hero keeping multi-million-dollar manufacturing operations from literally tearing themselves apart.
Because the fluid, it isn't just a byproduct or something to wash away the mess. It's a fundamental structural component of the machining process. Without it, the entire operation just grinds to a halt in seconds.
Okay, so let's unpack this. Because to truly appreciate the liquid, we kind of have to understand the beast it's trying to tame, right?
Definitely.
Why is a five-axis machining center so much more demanding than a standard, simpler machine? Like, what is actually happening to the metal in there?
Well, picture a traditional, simpler machine, right?
Okay.
You have a cutting tool spinning and moving along three basic axes, X, Y, and Z.
Right, so up, down, left, right, forward, back.
Exactly. It's relatively predictable. But in a five-axis machine, you're adding two rotary axes into the mix. So the tool, or even the massive block of metal you're cutting, is aggressively tilting and rotating while it's being machined.
So the contact zone, like the exact microscopic point where the spinning metal tool is violently shearing away the metal workpiece, it's never staying in one place.
Never. It's constantly moving. The tool is spinning at tens of thousands of revolutions per minute. The angle of attack is constantly pivoting. And because of that extreme continuous motion, the friction and the heat generation are just immense.
Wow.
We are talking about temperatures at the cutting edge that can easily exceed 1,000 degrees.
1,000 degrees.
Oh, yeah. And if you don't have a highly engineered fluid intervening at that exact microscopic point, the operation faces catastrophic consequences. I mean, severe thermal drift is one of the biggest threats here.
Thermal drift, meaning the heat actually causes the metal workpiece to physically swell and expand while it's being cut.
That's it, yes. If the metal expands even a fraction of a millimeter while the tool is shaping it, your dimensional accuracy is completely ruined.
Oh, wow, right.
Yeah, a turbine blade that is off by a hair won't fit into an aircraft engine. And beyond that, you're facing severe tool wear, where the expensive cutting bits literally melt or shatter.
Which means downtime.
Crippling downtime for a machine that costs thousands of dollars an hour just to run.
For you listening, this is where we really have to zoom in. It's not enough to just know the machine is complex. We have to look at what the fluid is physically doing at that exact point of impact.
Right, and this is where we see the dual role of the fluid. It's performing two distinct and sometimes seemingly contradictory jobs simultaneously. It has to cool and it has to lubricate.
Well, the cooling part makes intuitive sense, right? To control that thermal drift you just mentioned. The sources point out that water-miscible fluids, meaning chemical concentrates that are mixed with a large volume of water, they're generally much better for heat removal than straight, pure cutting oils.
Yeah, because water is incredibly efficient at transferring heat. It has a very high specific heat capacity, meaning it can absorb a massive amount of thermal energy from that glowing cutting edge before it actually boils.
Right, but water on its own brings a whole host of problems.
Oh, it does.
It causes rust, for one.
Massive rust. And more importantly, water is terrible at lubrication.
Right.
Lubrication is the second crucial job. You have to reduce the friction between the cutting edge of the tool, the chip of metal being violently carved away, and the workpiece itself. This is especially vital during heavy milling, deep hole drilling, or when you are machining really difficult, tough materials.
So to get that lubrication, the fluid is packed with extreme pressure and anti-wear additives. But I need to stop here because I'm struggling with the physics of this. If the tool is spinning at 20,000 RPM and generating immense pressure as it smashes into a block of titanium,
Yeah.
how does a liquid actually survive that? I mean, shouldn't the extreme pressure just instantly squeeze the fluid out of the way, leaving metal grinding on metal?
That is a brilliant question, and it gets right to the heart of how these extreme pressure additives actually function. They don't just sit there like a wet puddle.
Okay.
Under the immense heat and pressure of the cutting zone, these chemical additives actually react with the metal itself. They bond to the surface of the tool and the workpiece, forming a microscopic solid chemical salt film.
Wait, really? So it's not even a liquid anymore at the point of contact?
Not exactly, no. That solid chemical film acts as a sacrificial layer. It prevents the metal tool and the metal part from physically welding together under the pressure. It shears away instead of the metal shearing away.
That is incredible. But here's where my brain sort of short circuits again. In a 5-axis machine, the tool angle is always changing, tilting, spinning. Trying to get this highly engineered fluid to that exact constantly moving microscopic friction point feels like trying to water a specific leaf on a plant that is spinning inside a tornado.
That's a great way to picture it.
Right. So if you just have a nozzle spraying fluid into the machine, how does it even hit the target?
Well, it might not. If the tool tilts away, a fixed external nozzle might just be spraying fluid uselessly against the back of the heavy metal tool holder,
Just completely blocked.
completely blocking the fluid while the actual cutting edge on the other side is burning up. This is why the physical properties of the fluid, specifically something called wetting ability, are just as critical as the chemical makeup.
Wetting ability meaning how well it spreads out.
Yeah, think about water droplets on a freshly waxed car.
Okay.
They beat up into tight little spheres because of surface tension. You do not want that in a machine.
Right, that makes sense.
The fluid contains special surfactants that drastically lower the surface tension, allowing it to flatten out, cling to the spinning tool, and physically penetrate into those impossibly tight, moving microscopic spaces.
But the machine delivery system obviously has to step up here too, right?
So absolutely. A fluid can only do so much on its own. The machine architecture has to force the issue. Advanced 5-axis machines use through-spindle coolant.
Through spindle cool.
Yeah, they literally pump the high-pressure fluid right down through a hollow channel in the center of the spinning tool itself. So the fluid blasts directly out of the tip of the cutter, guaranteeing it reaches the exact point of contact no matter how much the tool tilts or rotates.
Okay, but what happens if that delivery fails? Say a chip of metal blocks the internal channel, and the coolant is just splashing the tool irregularly.
Irregular coolant flow can actually cause worse thermal shock than simply running a qualified dry process with no coolant at all.
Wait, how is a splash of coolant worse than no coolant?
Well, think about taking a piping hot glass out of the dishwasher and immediately running freezing cold tap water over it.
It shatters instantly.
Exactly. The exact same thermodynamics happen to a solid carbide cutting tool. If the coolant delivery is stuttering, the cutting edge repeatedly heats up to a glowing temperature in the cut and then gets splashed with cool liquid a fraction of a second later.
Ouch.
Yeah, that extreme thermal cycling causes the cutting edge to rapidly expand and contract until it develops microcracks. Ultimately, the tool fails violently, snapping off right in the middle of a cut.
Okay, so we've established the physics. You've successfully blasted this chemically loaded fluid into a microscopic, superheated collision.
Right.
But what actually happens to the metal at that exact millisecond of impact? We have to look at the chemistry tightrope here. Because reading these sources, it just blew my mind that a fluid engineered to perfectly cut a block of steel could actually ruin a different metal entirely.
What's fascinating here is just how delicate this chemical balance really is. Fluid engineers are constantly threading a needle. A fluid that is chemically aggressive enough to protect raw carbon steel from rusting and provide the heavy lubrication it needs, well, it might completely stain and oxidize an aluminum aerospace part, turning it black.
Wow, let's break down these material realities because the sources are incredibly specific about what different metals demand from this liquid. Let's start with aluminum.
Okay, so when you look at aluminum, you're dealing with a metal that is fundamentally soft and sticky. It conducts heat well, but under the friction of cutting, aluminum actually wants to melt and physically weld itself to the cutting tool. This is called built-up edge.
And if the aluminum sticks to the tool, you're no longer cutting with a sharp edge, right? You're just bludgeoning the part with a blob of melted metal.
Exactly, which ruins the part instantly. So for aluminum, the fluid needs massive cooling properties to keep the temperature below that welding threshold, along with moderate alkalinity and non-active chemicals that won't stain the soft surface.
Right. But moving to stainless steel, the dynamic completely shifts. Stainless is tough, and it's prone to something called work hardening.
Yes, stainless steel actually gets physically harder the more you cut into it and deform it.
That sounds like a nightmare.
It is. Because of that immense resistance, your fluid suddenly needs incredibly high extreme pressure and anti-wear performance to form that sacrificial chemical barrier we talked about earlier.
Okay, and then there is cast iron. This one really surprised me. The sources point out that cast iron doesn't really form nice, clean chips when you cut it. It shatters into this incredibly abrasive, fine graphite powder.
Yeah, that powder is a nightmare for a fluid system. If your fluid can't capture and control those microscopic fines, that powder gets suspended in the liquid and essentially turns your expensive coolant into a high-pressure liquid sandpaper.
Yikes.
Yeah, completely destroying the machine's pumps and valves.
And finally, titanium, the heavyweight of aerospace.
Yeah.
It generates incredibly concentrated heat right at the cutting edge because it doesn't conduct heat away into the chips like other metals do.
Right, it just holds the heat like a furnace. So titanium demands aggressive cooling, incredibly high lubricity, and very low foam delivery so the liquid can actually reach the cut.
And while the fluid chemists are frantically balancing all of those metallurgical demands for the metal being cut, they also have to worry about the multi-million-dollar machines surrounding the entire process.
Oh yeah, the collateral damage.
The collateral damage, right?
It's very real. A 5-axis center is full of highly engineered elastomers, rubber seals holding back pressurized hydraulics, flexible hoses, high-tech paint, polycarbonate safety windows, and incredibly sensitive measuring probes.
A lot of delicate parts.
So many. And a chemically aggressive fluid might cut titanium beautifully, but over the course of 6 months, it could slowly melt the machine's internal seals, strip the paint off the inner walls, or cloud the safety windows so badly the operator can't see inside.
So you say the titanium part, but you slowly digest the machine making it.
Basically, yeah. Machine tool builders and fluid suppliers actually run extensive month-long compatibility tests before a new factory goes into full production.
Wow, months long.
Yeah, they soak the machine's specific rubber seals in the fluid just to ensure the liquid won't attack the machine's internal nervous system.
And we can't forget the human element either. The fluid has to be safe for the operator standing 3 feet away. It needs to have low odor, controlled misting, and comply with strict health and safety regulations.
Absolutely.
I mean, a factory cannot have a fluid that aerosolizes into a toxic fog every time the spindle spins up.
Operator safety is paramount. If a fluid causes dermatitis or respiratory issues, it's pulled from the line immediately, regardless of how well it cuts metal.
Which makes total sense. But here's where it gets really interesting for me. Finding this perfect chemical balance is a massive triumph. You've matched the physics, you've matched the chemistry for the metal, the machine, and the human. You fill up the massive tanks, you hit start on the machine, and the moment you do, that beautiful, perfect fluid begins a slow, microscopic process of dying.
It does. A cutting fluid sump is a living, breathing ecosystem, and from the minute it mixes with water, it is constantly under attack.
Yeah, reading through the maintenance section of these sources, I immediately thought about keeping a delicate saltwater aquarium alive.
That's a perfect analogy.
Right. If you just fill a high-end aquarium with perfectly balanced water and walk away, within a week, the invisible chemical markers drift, the pH crashes, things start smelling awful, and everything inside goes belly up. The fluid in a 5-axis machine is exactly the same. You cannot just fill it and forget it.
No, you can't. Daily maintenance is absolutely non-negotiable for a factory. The operators have to check the fluid level, the chemical concentration, the pH, the odor, foam levels, and chip accumulation.
Every single day.
Every single shift.
Wow. Let's talk about the mechanics of measuring this, because it's not as simple as just eyeballing the tank.
Yeah.
To check the concentration, meaning how much of that complex chemical concentrate is actually mixed into the water, you have to use a handheld optical tool called a refractometer.
Yes.
How does this actually work?
Well, a refractometer measures how much light bends or refracts as it passes through a liquid. When you put a drop of the machine fluid on the glass prism and hold it up to the light, the dissolved chemical particles in the fluid slow down and bend the light.
Okay, so it creates a visual marker.
Exactly. The denser the fluid, the more the light bends, which projects a distinct shadow line onto a numbered scale that you read through an eyepiece.
But the number you see on that scale isn't the actual concentration percentage.
No, and that is a incredibly common and costly mistake in machine shops.
Oh, I bet.
The scale just measures generic refraction. You have to multiply that reading by a specific refractometer factor provided by the chemical manufacturer for that exact fluid.
Because they're all slightly different.
Right, some fluids bend light differently than others. If you forget to multiply by that factor, you might look through the eyepiece and think your concentration is a perfect 5%, when in reality, it's dangerously low.
Which means the rust protection fails and the tools start burning up.
Exactly.
Or conversely, you think it's fine, but it's actually way too concentrated, which costs a fortune in wasted chemicals, causes skin irritation for the operator, and creates massive farming issues.
Accurate measurement is the only way to survive.
Yeah, and when you inevitably measure a low concentration and have to add more fluid to top off the tank, there's a very specific mixing rule that felt straight out of a chemistry lab or like a bakery.
Oh, yeah.
You always add the chemical concentrate into the water. You never pour the water into the concentrate.
Yeah, if you pour water into a bucket of pure oil concentrate, you risk inverting the emulsion.
Inverting the emulsion. What does that look like physically?
So, cutting fluids are designed to suspend microscopic droplets of oil evenly throughout a large body of water. If you do it backwards, if you dump a small amount of water into a large pool of oil, the chemistry gets confused. Yeah. The oil tries to suspend the water instead. It clumps up, it forms a thick mayonnaise-like sludge that won't mix properly, and you completely ruin the chemical structure of the fluid. You always have to slowly introduce the concentrate into a large body of agitated water.
It's exactly like tempering chocolate or slowly whisking hot butter into egg yolks.
Exactly.
If you dump it all in at once or do it backwards, you just get a scrambled, broken, ruined mess.
It's the exact same principle of emulsion, yeah.
Okay, but even if you mix it perfectly, even if your refractometer readings are flawless,
Yeah.
you have this relentless enemy waiting in the tank. Tramp oil.
Tramp oil.
Yeah, I need to push back here for a second. If this is a multi-million-dollar ultra-precise machine, why is it leaking its own oil into the coolant tank in the first place? Shouldn't these systems be perfectly sealed?
I mean, in a perfect world, yes. But in reality, a 5-axis machine is composed of massive cast iron components sliding back and forth on linear guideways at incredibly high speeds.
Right.
Those moving metal-on-metal parts require constant, heavy mechanical lubrication. Whey oil, hydraulic fluid, spindle oil. Despite the best seals in the world, as the high-pressure cutting fluid blasts around the inside of the machine, it inevitably washes some of that heavy lubricating oil off the internal rails and carries it down into the main coolant tank.
So it's an unavoidable mechanical reality. What happens when that tramp oil gets into the tank?
Well, it floats to the top and creates a thick, unbroken slick on the surface of the cutting fluid. The real danger is that this oil slick acts like a lid. It completely seals off the fluid, preventing oxygen from transferring from the air into the cutting fluid below.
And when you cut off oxygen to a warm, wet, dark environment full of organic material and metal dust,
You create the perfect breeding ground for anaerobic bacteria,
the bad kind of bacteria.
the worst kind for a factory. These bacteria thrive in environments with zero oxygen. As they rapidly multiply in the dark tank, they literally eat the organic components of the cutting fluid, breaking down its chemical structure.
Just digesting the coolant.
Yeah, and as they digest the fluid, their biological byproduct is hydrogen sulfide gas.
That classic rotten egg smell.
Exactly.
I've walked past machine shops where you can catch a whiff of that rancid smell right from the sidewalk. That's a dying tank.
That's a tank that has gone septic. To prevent that, factories have to use mechanical skimmers, like little belts or wheels that dip into the tank, to constantly pull that tramp oil off the surface and let the fluid breathe.
You also monitor this microscopic war by reading the pH of the fluid, right?
Yeah.
Because the pH tells a story of what's happening invisibly in the tank.
Right. A falling pH is a massive red flag. Cutting fluids are naturally alkaline, usually sitting around a pH of 9. If that number starts dropping towards neutral, it almost always indicates that bacterial activity is ramping up, producing acidic byproducts that are eating away at the fluid's built-in alkaline reserve, or it simply means your concentration has dropped too low.
Okay, and if the pH is suddenly rising?
A rising pH is rarely biological. It usually means human error. Someone added way too much raw chemical concentrate without measuring, or worse, an operator dumped raw alkaline additives into the tank trying to quickly fix a rust problem.
Oh boy.
A sudden spike in pH can instantly create severe skin hazards, chemical burns for the operators, or cause the fluid to suddenly start severely corroding those sensitive aluminum aerospace parts we discussed.
It's a total high-wire act. And frankly, playing the role of a factory manager looking at a massive spreadsheet right now, if maintaining this perfect fluid requires so much obsessive, daily, microscopic care, I'd be incredibly tempted to just bypass the headache.
Oh, I'm sure.
Why wouldn't a factory manager just buy the absolute cheapest fluid possible, skip the refractometers, and just dump the tank and replace it every week when it gets dirty?
Well, if we connect this to the bigger picture of manufacturing economics, that logic is the ultimate trap.
Really?
Yeah, the actual price a factory pays for a barrel of chemical concentrate is the smallest, most insignificant part of the total operating cost. Buying cheap fluid to save a few bucks is stepping over dollars to pick up pennies.
I need you to break that down. Where are the hidden costs hiding?
Let's go back to the physical realities we discussed earlier. Say your cheap budget fluid doesn't have good wetting ability. It beads up. Because of that, it lacks the physical pressure and flow to evacuate the metal chips out of a deep cavity being drilled in a part.
Okay.
What physically happens? The machine doesn't know the chips are still in the hole. It just keeps moving. The tool comes back around and smashes into a pile of hardened metal shavings it just cut a millisecond ago.
Oh, it's recutting its own chips?
Exactly. And those work-hardened chips act like aggressive sandpaper. They get dragged around the part, instantly scratching the mirror surface finish of a critical aerospace component, meaning that part is permanently scrapped.
Oh, okay.
And the impact physically chips the microscopic edge of the cutting tool, instantly destroying a piece of tooling.
So a few pennies saved on a gallon of cheap fluid just cost the factory a $200 solid carbide tool and a $5,000 piece of scrap titanium.
Precisely. And let's look at the mechanical issue of foam. Cheap fluids, or fluids lacking highly engineered anti-foaming agents, will froth up like a bubble bath under the violent high-speed circulation of a 5-axis machine.
Right.
If that foam gets too thick in the tank, the main coolant pump actually starves.
How does foam starve a pump?
Well, the pump relies on sucking in heavy, dense liquid to push through the lines. When it sucks in foam, it's grabbing air. Air compresses. This is called cavitation.
Cavitation.
The pump spins, but it physically cannot push the aerated fluid through the tiny internal spindle passages. Suddenly, right in the middle of a heavy cut, the coolant delivery stutters and stops.
Yeah, we know what happens next. The tool temperature spikes, the metal expands, thermal shock shatters the cutter, and the machine goes down.
Yep. The real expenses in manufacturing are never the fluids. The real expenses are the tool failures, the scrapped parts, the emergency manual cleanouts when a tank goes septic, the massive environmental waste disposal costs of pumping out and treating thousands of gallons of dead fluid, and most importantly, machine downtime. A 5-axis machine that isn't cutting metal is burning money at an astonishing rate.
So what does this all mean for a modern factory? I mean, the solution isn't cheap fluid. The solution is investing in automated systems that protect the good, highly engineered fluid.
Exactly. And this raises an important point about modern factory design. Staged filtration is vital. You cannot just use a single mesh screen for everything. To protect the fluid, factories use magnetic separators to automatically pull out the ferrous steel chips, combined with complex hydrocyclones.
Hydrocyclones.
Yeah, they are conical devices that use centrifugal force. They rapidly spin the fluid, forcing the heavier non-ferrous fine powders like aluminum or that abrasive cast iron dust to the outside walls where they drop out of the fluid entirely while the clean fluid spirals up the center and back into the machine.
That's brilliant.
It is. You pair that kind of advanced filtration with automatic dosing systems that pull concentrate and water perfectly on demand.
Which completely takes the human error out of that baking equation we talked about earlier. No one is manually dumping water into a bucket of oil by mistake.
Exactly. And the only true way a facility can measure these total operating costs is through a rigorously controlled trial period. You run the highly engineered fluid on representative materials, you meticulously track the tool life, the surface finish of the parts, the biological condition of the sump, and the reduction in downtime. And you let the data prove that the more expensive fluid is actually saving the company tens of thousands of dollars a month.
It is entirely an ecosystem approach. So for you listening, let's pull all of this together. We've seen that cutting fluid isn't just a dirty byproduct. It isn't just an accessory you pour into the machine like windshield wiper fluid.
Not at all.
It is a vital, living, structural component of a 5-axis machining center. It sits dead center at the intersection of extreme thermodynamics, metallurgy, delicate chemistry, and factory economics.
It really is the critical connective tissue between the machine, the tool, and the final product.
It truly is. Which leaves me with a final thought for you to ponder, something that builds on everything we've unpacked today. Consider just how much of a multi-million-dollar 5-axis machine's entire architecture, like the complex rotary joints, the high-pressure internal spindle passages, the specific chemical-resistant seal materials, the massive staged filtration tanks taking up huge amounts of factory floor space.
It's massive.
Right. All of it is engineered purely to accommodate the fluid, not the actual cutting of the metal itself. The machine is practically built around the liquid. So if material science and tooling technology eventually advance enough to eliminate the need for liquid coolants entirely, how radically different, and perhaps impossibly small, will the manufacturing machines of our future look?
That is a fascinating question. I mean, take away the fluid and you change the entire physical paradigm of modern manufacturing.
Something to keep in mind the next time you see a piece of perfectly machined metal. Thank you for joining us on this deep dive, and as always, keep questioning the invisible engineering around you.